Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about the Zener Diode, so let's get started. Alright everybody, so let's talk about the Zener Diode, shall we? Now, I made a drawing here about the Zener Diode electrical characteristics, right? So first off, I want to talk about the symbol, all right? And I drew it here. And if you compare it to the regular diode, how we were drawing it, if we go left to right instead of up and down, it would look like this, right? This would be your positive voltage. This would be your ground. You would obviously have to have resistors in here, but the current flow, conventional current flow, was this way. It's almost like it pointed, right? But if you're talking about a Zener diode, the Zener diode points in the opposite direction to current flow, doesn't it? Well, you don't know that. You gotta trust me on that. It does, right? So here's your plus voltage and here's your ground. All right? And what you have here is you have a something like this. It looks like a Z, right? What I did is I drew it here. I drew it up and down instead of left to right. And your positive voltage would be here and your ground would be this way. Now remember, again, there could be other things in the circuit. I just wanted to basically emphasize here that your symbol is slightly different than the diode, and is that it has these little wings here on it, right? The other thing I wanted to emphasize is that it's operated in reverse bias, all right? So if you recall with the diode generally, if you remember your I, if this is your I axis right here, and that's forward biased, and then this is your forward bias here of your voltage. You would come through here until it reached about 0.7 volts, and then it would just shoot right up, right? Now, when you operate them in reverse, it would come this way, and then obviously you would reach breakdown and do this number, right? And this was your current. I'm not drawing as straight as I should. This is your current. You're going in reverse, all right? So what I've done is I've taken this chart that I just drew for you, and I just drew the reverse portion of it, okay? And the reverse portion of it shows what happens. Your current here is in blue, as you can see, and it's your voltage is on the x-axis. This is getting more negative. It's reversed biased, okay? So, and your current is negative too in its direction, right? So there are three things you need to understand. You have the Z, IZ, which is your test current, and that corresponds to your Zener diode voltage, okay? That's equal to VZ. You also have two other currents, IZK and IZM. IZK, this is the minimum current required for the Zener diode to regulate a voltage or operate correctly, minimum current. And IZM, this is your maximum current. And this is also known as your test current. C-U-R-E-N-T. You get the idea, right? So the thing is, when you pick up a Zener diode, it's going to have this information, right? It's going to have the Zener current, IZ, and it's going to have it at a specific value, VZ. Okay? So that basically is one of the first things I wanted you to understand about the Zener diode. Now, look at this line, this blue line, this current. This IZK, this point right here, basically is where this line starts to become linear. So in other words, it's come across the knee. This is known as the knee right here. This area right here can be thought of as the knee, just like you're sitting at a table and bending your leg. And then when it becomes straight, okay, that starts your IZK. And IZM is just the maximum current. When you exceed that maximum current, you could damage the diode because you've reached breakdown, all right? And it's a good cascade, which would mean it would heat up the diode and then bad things would happen, okay? So, but let's talk about this line. What do we have? We have a change in voltage and a change in current taking place at the same time, right? So this is a critical factor. So this is called ZZ. And this is equal to your change in V divided by your change in current, which is I, all right? Now remember Ohm's law? V equals IR. Well, basically, R is equal to V over I, right? So you can see that ZZ can be thought of as a resistance, okay, in this case. So that's what we're talking about. So when you have a Zener diode, you're going to have these characteristics, and you can solve some very useful problems in its operation. And that is what we are going to do next. So see you shortly. So everyone, let's continue with our discussion, but before we get into the Zener diode problems of current, I want to address the temperature coefficient characteristic of the Zener diode. Now this is important because, think about it, the characteristic of why Zener diodes are so important, though, is it will maintain a specific reverse bias voltage. So you can buy Zener diodes in many flavors. You can get them in 10 volt, 5 volt, 15 volt, with different number of voltages that you want. Okay? So the reason why you get them is because you want to hold something to a specific voltage. You don't want it to change, okay? So one thing that can affect the change of the Zener diode voltage is the temperature of it. So you have to think of the environment where it's going to be operating. So generally there are two ways to express the temperature coefficient, and I've outlined them right here. One, okay, it's going to be in percent per degree C, all right? And number two is going to be in milliwatts per degree C. So let's do a problem of each so I can demonstrate how they're used, all right? So we have an 8.2 volt Zener diode. That means for problem one, I'm just going to write a 1 over here. We're going to say VZ, that's your Zener diode current. Or, I'm sorry, your Zener diode voltage. Remember, when your Zener diode, if this is I, and this is your voltage, remember it's in reverse. You have your voltage that's coming like this, and it hits the knee, and it comes down, and we're assuming it's linear here, right? And then you hit this area called IZ. That's your test current. And if you take it and you go straight up, you're going to hit VZ. That's where your diode is spec'd at, right? When I say spec'd, I mean it's specified to operate at that voltage with that current going through it at a specific temperature, okay? So that's what we're talking about, and then we want to see how this is going to change if the temperature changes, all right? So let's just take this little drawing and just move it over here, okay? So if your VZ is, let's just say your VZ is equal to 8.2 volts, okay? At 25 degrees C. That's about room temperature, okay? Now that it has a positive temperature coefficient. Now what does that mean? That means if you draw two arrows, they're going in the same direction. That means if temperature goes up, that means your voltage is going to go up. Got it? Same thing. If your temperature goes down, your voltage goes down. The key thing to remember here is they're going in the same direction. That's what we mean when we say positive temperature coefficient, okay? By the way, this is pretty universal. You can apply this to other coefficients as well. So I don't want to make a blanket statement, but generally that's what it's saying, okay? So we have a positive temperature coefficient, and that is going to be 0.05% per degree C, okay? So it's asking voltage. What is the voltage at 60 degrees C? That's your question. In other words, all else being equal, nothing changes. You're just going to change the temperature from 25 to 60. What's going to be your new voltage? So let's look what's going on here. What do we expect to have happen? It's a positive temperature coefficient. You know your Zener voltage, this value right here is 8.2 volts. Now, since this is in reverse bias, you might be asking yourself, why isn't it negative 8.2 volts? Well, technically you might be correct when you say that, but just understand when we're saying VZ is 8.2, we know it's 8.2 and it's negative in its polarity, but we're worried about the magnitude right now, okay? That's an 8.2 and that is a voltage. Now, if the temperature is going up, if T is going up, what's going to happen to V? Well, that's going to increase too because they have to go in the same direction, right? So how you find that out is you use the formula. There is a formula in many books, but what it's going to tell you is the change in VZ, delta VZ, all right? That's going to equal VZ, which you know that value, times your temperature coefficient, call that TC, times your delta T. Now watch your units. This is in degrees C. Let me get my thing in red here, all right? This here is in degrees C, isn't it? So make sure that the temperature you're using is in degrees C. If it isn't, you have to convert it, all right? Just be careful of that, right? So if we go back and we rewrite this, we can say this is going to be equal to 8.2 volts times, now this is in percent, we're going to have to convert it. It's going to be 0.0005, all right, This percent, you have to divide it by 100 to get rid of the percent, right? And that's actually per degree C times, well, your delta T. This is going to be 60 degrees C minus 25 degrees C. Got it? So this is going to be 35 right here, right? So I'm just going to just do this. I'm just going to say this is 35 degrees C, all right? Notice how we wrote it, that your degree C here cancels with your degree C here, right? So now, if you simply multiply that out, this is going to equal to 0.144 volts, which is equal to 144 millivolts. All right? Now, that's going to be the change. How do you apply it to your Zener? Remember, it's a positive temperature coefficient. So you would expect, if the temperature is going up, the voltage is going to increase in magnitude. So you would simply add it. But your voltage is going to be farther out this way. Get it? In this case, your voltage was increased, so you would simply add it. So it would be 8.2 plus 0.144 volts. That's going to equal 8.344 volts. Got it? So it would shift your voltage this way out. Your voltage would be there. Okay? Now if it decreased in temperature by 35 degrees, your voltage would go this way. Get it? All right, everyone. The next one, I'm going to clear this off and we're going to do another problem, but we're going to use a type 2 temperature coefficient. See you in a minute. All right, so the second problem, let's use this type right here, okay? This is going to be in milliwatts per degree C, because we already did this one and we understand it, right? So we're going to work on this one right here. So let's set up a problem. A certain Zener diode has a maximum power rating. All right, let me just do what I did before. Here's your second problem. And your Zener has a power rating of 400 milliwatts at 50 degrees C. It's kind of warm, isn't it? This 25 degrees C is room temperature, so that's going to be warmer. And it has what's called a derating factor of 3.2 milliwatts per degree C. Get it? So it wants to know, or the question wants to know when I say that, is determine the maximum power the Zener can dissipate at 90 degrees C. So we have a 90 degrees C. So what's the power it can dissipate? I'm going to just put dissipation power with a question. Dissipation power equals, we don't know. That's what we got to figure out, okay? So in these kind of problems, think about it for a second. It can dissipate 400 milliwatts at 50, and we're increasing the temperature, right? So think about it. If you're outside and you're walking, and suppose you can dissipate so many degrees, you can stay cool, right, at a certain amount at this temperature. As the temperature gets hotter outside, it's going to be harder for your body to stay cool, right? So you're not going to be able to dissipate as much, right? If you if you're running or something like that and generating the heat for your body. So the delta T here is 40, right? Delta T equals 90 degrees C minus 50 degrees C equals 40 degrees C, right? So your temperature has increased by 40, right? And we know that we can dissipate 3.2 milliwatts per degree C, right? Times 40 degrees C. And this is going to equal how much you can dissipate, right? I'll call it dP just for short, right? Now this is going to equal, you multiply that out, that's going to equal 128 milliwatts, right? This is a W, by the way. Doesn't look like a good W, but that's a W, all right? So if we get back to our example, what do we do with this 128 milliwatts, right? You know that you can dissipate 400 at 50, but now the temperature is increased. Well, you're not going to be able to dissipate 400 now, so this is going to be subtracted, right? So it's going to be 400 milliwatts minus 128 milliwatts equals, that's going to be 272 milliwatts, right? Now what would happen if instead of it went to 90, suppose it went to 10 degrees Celsius? In other words, your delta T would stay the same, but you would apply it differently. If it's cooler, that means it could dissipate more heat, right? So you would have added this and it would be 528, but for the 528 milliwatts, right? Think of it like going outside and running on a winter day when it's nice and cold or cool, let's say. It may not be that nice depending on how much you like to run. You could dissipate more heat that way than if you go out and you run on a hot summer day in the sun where it's almost 100 degrees outside, right? That's kind of what we're talking about here. So that is what I wanted to tell you about the Zener diode temperature coefficient. So be aware when you're looking at the Zener diodes, think of the environment where they're going to be used, all right? And make sure you apply these correction factors in your calculations. Okay, next we're going to start to do some Zener diode problems. See you in a bit. All right, so now let's try our first Zener diode problem, all right? So now, let's suppose that you're given a problem and you're given ZZ. Remember ZZ is the resistance, right? And that's, let's just say, is 3.5 ohms. Remember, we're talking about this right here, that slope of this line. And remember, the delta V, change in volts, over your change in I gives you ZZ, right? So remember that. Delta V divided by delta I is going to equal ZZ. And the problem, we're giving you that, right? You can get that from the data sheet of a Zener. So this is a good parameter. They measure that for you, right? So they're going to give you VZ, and for this problem, let's just say VZ, which is right here, is going to be 6.8 volts. 6.8 volts. Get it? Now, its associated IZ is 37 milliamps. All right? You got it? And that pertains right here. So you have ZZ, you have VZ. I guess it's 8.6 volts. I'll just call this, I just write it there. That's VZ, okay, just so you know. And then this is IZ over here, and they give you IZ, right? So it's going to ask you, what is the voltage across the Zener diode at when the current equals 50 milliamps? So if IZ increases, you know, this direction here, IZ gets smaller. Because when it crosses the axis, this is 0. Got it? But in this direction, it gets larger. IZ larger. So suppose, remember, IZM is the maximum Zener, so maximum Zener current it can handle. So let's suppose that the 50 milliamps is, say, right here. This is your 50 milliamps. Right there, okay? So it wants to know what the new voltage is, right? Up here, right? If you draw this line across here. By the way, when you do these problems, I highly suggest you draw this curve and you draw it, because when you visualize it, it makes it a lot easier for you to see. So you want to know what the new voltage is. Doggone it, I didn't draw that too well, did I? Oh well, let's try again, huh? There it is. I'm going to start it. We're going to draw right from there. We want to know what that new voltage is, right? V, I'm just going to put a question mark. We don't know what it is. That's what we need to find out, right? So the first thing is, let's find out what delta I is. Delta I is the difference between this current and this current. I'll just write a delta I right here. Let's get over here, we have more space. So delta I is going to equal 50 milliamps minus, that's an A, 50 milliamps minus 37 milliamps, which is going to equal, guess, 13 milliamps, right? Now that should make sense, right? We have the 13 milliamps difference in current, right? Now, what else do we know? Don't we know this right here? You know your ZZ, don't you? What's Ohm's law? V equals IR. So we know this, don't we? That is right there is 13 milliamps. Don't we know that, right? R, well, if we're coming up here, we said ZZ is, this is very similar to R, so it's 3.5 ohms, right? 3.5 ohms. That's a 3. Okay? So when you multiply those two together, that's going to equal, right, 45.5 millivolts. Or that's going to be equal to 0.0455 volts, okay? So you know the change in voltage. That's your delta V. Get it? So what are you going to do? You know it's going to be on this side of your 6.8, don't you? So you're going to basically take VZ, which is going to be your 6.8 volts, plus your 0.0455 volts, and that's going to equal 6.845 volts. And that's your new voltage that is right there, okay? My handwriting's not great, I'm not going to rewrite it, but you see what happened? It moved your voltage over there a bit, right? Now we could do something very similar here. In fact, why don't we do it, right? Suppose you wanted to figure out, do the same problem, but you want to say, hey, the new current is going to be 25 millivolts. So suppose we have one right here, right? I'm sorry, 25 milliamps. I'm sorry. The current's 25 milliamps. Sometimes when I'm writing and I'm talking, I get tongue-tied here. Sorry about that. So this is going to be 25 milliamps, right? So for this problem, I'm going to write it over here. We have your delta I is going to equal 37 milliamps, right? Because that's your IZ, and you know what V is to that, a reference to there, minus your 25 milliamps. That's going to equal 12 milliamps. Got it? So you know your change in I. You also know this voltage right here, right, is 3.5. So your voltage, say delta V, is going to equal, I is going to be 0.012 amps. That's 12 milliamps, right? Times 3.5 ohms. And that's going to equal, so let me do this on my calculator here real quick. That's going to be 42 millivolts. Which is equal to 0.042 volts. Get it? Now, how do you apply it? Well, this is on the other side, isn't it? In other words, your voltage is going to decrease in magnitude, isn't it? It's not going to be, it's going to be less than your 6.8, isn't it? So this is going, so your voltage, your new V, you know, your new voltage is going to be 6.8 volts minus 0.042 volts, right? Which is going to equal 6.76 approximately volts. And that's this voltage right here that you just, right there. So after that problem, you can see the technique is pretty much the same, right? You have to determine your change in current, your delta I, and then once you determine your delta I, and if you draw it like this, you will know what side of VZ your new voltage is going to be, right? Another way to look at it, if your current's increasing, obviously you're getting as a higher magnitude, it's going to increase the voltage. If your current has a smaller magnitude, it's going to decrease your voltage, right? But whatever that is, that change in current, you multiply it times ZZ, and that's going to give you your voltage, and you just add it or subtract it to your Zener voltage, and you have it. All right, so let's try another problem. See you shortly. All right, so let's try another problem. Now in this problem, you're given a circuit, and I drew the circuit right here, okay? So you can see it. You have a voltage here, through a battery. You're going through a resistor, right? You have a Zener diode here. Gotta draw that right. I gotta make sure I don't forget to put those little wings on there. And then you have your output voltage. This is ground. It's the terminal here, and here's your V out, right? And the problem is we need to know the minimum and the maximum input voltages that can be regulated by the Zener diode with this circuit, okay? That's the question. Now, what's been given to you, I circled in blue, or put a box around in blue, okay? So, actually, right here, I should put a box around that because that was given to you. All right? Now let's go back and just start thinking. What's one of the first things we need to do? We need to find out the voltage at both IZK and IZM. So let's start out at IZK, all right? We'll just do the minimum first. So we're going to say at IZK, right? So this is what we're going to work on. So we know, we just did this in the prior problem. Delta I is going to equal, well, we know IZ is 49, right? And we know IZK is 1 milliamp. And so delta I is going to equal 49 milliamps minus 1 milliamp. That's going to equal 48 milliamps, right? And we know what ZZ is right here. It's 7 ohms, right? So if we want to find out that delta VZ, just the change, that's going to equal 48 milliamps times 7 ohms, right? And that is going to equal, let me see what that's going to equal. Volts. Okay? Seven times 7, that's correct. Yep, I just had to do that in my head. Okay, so now we have to apply that, right? So we're going to say the new VZ is, okay, right, the knee, that's going to equal 5.1 right? And that comes from up here, right? That's VZ. Now, since we're looking here, we know it's going to shift in this direction, so it's going to be smaller. So we're going to subtract 0.336 volts, right? Now, if you do that, you're going to come to a value of 4.76 volts, all right? So that's going to be this voltage right here. That's what you just figured out. Now, what we're saying then, if we come over here to this picture right down here, this is going to be 4.76 volts here. Got it? This Zener right here can maintain 4.76 volts as long as it has 1 milliamp of current going through it this way, right? So let me write that over here so you have more space. 1 milliamp. Okay? Now, that's 4.76. We have 1 milliamp of current going through a 100 ohm resistor, right? So that's going to be, you have to take in this into account, right? So if you want to know the voltage drop here, you have 1 V, let me write this down. The voltage drop across R, right, in this, what we've just said, is going to equal I times R. This is going to equal 1 milliamp times 100 ohms, right? So 1 milliamp, all right, which is 1/1000th of an amp times 100 ohms, is going to be 0.1 volts, right? 0.1 volts, okay? So now you want to get the voltage that has to come in here. It's going to have to be higher, right? Because you're going to have something that's lost. Now what you have is you have what you need to figure this out, okay? So if you know the value of the, if you know the voltage at this point up here, which you do, it's right here, right? It's 4.76 volts. You know you're going to drop 0.1 volts here. You know you have to start out with 4.86 volts. You simply add the 0.1 volt to the 4.76. That's what you have to start out with. So that's your minimum voltage. So your minimum voltage for regulation is going to equal 4.86 volts. Got it? Now, let's figure out the maximum. Okay, I just neatened some things up here. So now let's do the other part of the problem. To get the maximum voltage, you need to find out this number. What is IZM equal to? Because we don't know. It wasn't given to us, right? So here's a trick you need to know for these kinds of problems. In this case, you're given a power dissipation, okay? That's really something important that you need to be able to understand. So for this specific diode, there's one thing here I didn't put down, I'm going to tell you. So it has a power dissipation of 1 watt, okay? 1 watt. Now let's start here, shall we? Our power dissipation, that's given to you, okay? Now if your power dissipation is 1 watt, let's think for a second. Power is equal to volts times current, isn't it? Right? So we know what the voltage is at Z. It's going to be 5.1 volts times I is going to equal messed that one up. It's going to equal 1 watt. So this is going to equal 1 watt, okay? So if we rearrange, basically, that's going to equal 1 watt divided by 5.1 volts, and that's going to be equal to 196 milliamps. Okay, so there's your IZM. We can put it over here, 196 milliamps. I'm not going to put a box around it in blue because you weren't given that. You were given this. So remember, if you were given this, you can determine what IZM is, okay? So pretty much we have to do the something similar. So we're going to have to find out the change in voltage, right? So why don't we do that over, let's do it over here, why not? We have IZM minus IZ is equal to delta IZ, right? This is going to be 196 milliamps minus 49 milliamps. That's going to equal, let me see, I'm doing this in my head. This is going to be equal to 151.47 milliamps. Is that right? 4 subtract 9, that's 50. 47, that's right. Okay. Now, you're going to take this 147 milliamps, that's your delta Z. We're just going to do the same thing we did before, right? You're going to find out your new VZM is going to equal VZ plus this change here. It's going to be equal to 147 milliamps times 7 ohms. That comes from up here, right? That hasn't changed. This is going to equal 5.1 volts plus the second, let me do this right now, 1.03. That's going to equal 6.13 volts, all right? That's your new voltage right there. So this is your VZM, and this is your VZK, right? This is great. You know now how to figure out what these two voltages are. So what's your new voltage? It's going to be what? 6.13 volts, right? What's your current? Your current is going to be right here, going through here. I equals 196 milliamps, right? Milliamps, okay? So if you take your 196 milliamps and multiply it times 100 ohms, right, and add it to this value, you're going to have the voltage you need to start with, aren't you? Well, if you do that, let me write it down for you. So your voltage you're going to need, your VN, to do this is going to equal, what's it going to equal? It's going to equal your 196 milliamps times 100 ohms, got it, plus your 6.13 volts, right, which we just calculated. And if you want to know the result, that's going to equal 25.7 volts, okay? So if you look at it, your minimum voltage was 4.86 and your maximum voltage is 25.7. So there's quite a voltage range where that's going to be able to keep the voltage close to 5.1 volts. As you can see, it's not perfect, right? But it's pretty good. It's pretty good. All right, everybody. That is the next problem. So let's try another one. There's another type I want you to be able to do. So I'll see you shortly. All right, everyone. One last problem here. So I drew out the circuit, right, which is again right over here. And this time I gave you a voltage. We have a 12 volt Zener, so this is 12 volts. we know R, which is 470, right? And we want to find out RL, all right? So we were told to make things simple in this problem that ZZ is equal to 0. So we don't have to worry about that. We can just assume that VZ stays to be. So we were told that ZZ equals 0. So we can just assume that the Zener voltage stays at 12 volts regardless if you're at IZK and IZM to make things simple. So that's why we have 12 volts here. All right? IZK is 1 milliamp and IZM is 50 milliamps, right? So let's just think about this right now, okay? If you have, we want to figure out the current coming in, don't we? So what's your current coming in? I in is going to equal V over R. This is your voltage drop. This is going to be 24 volts minus 12 volts divided by 470 ohms. Get it? That's coming right from here. Okay? Now if you calculate that out, you're going to have 25.5 milliamps. Now if you have 25.5 milliamps coming in, okay, for minimum regulation you need to have 1 milliamp going through your Zener. 1 milliamp, right? That's what this is telling you right here, 1 milliamp. So if 1 milliamp is going through your Zener for regulation, how much do you have left? Well, 25.5 milliamps minus 1 milliamp equals 24.5 milliamps. Got it? And that is going to equal the current through your load resistor right here. So what do you know? You know the voltage and you know the current. What can you calculate? Well, I think you've probably already figured that out. So R is going to equal V over I, right? Which is going to equal 12 volts divided by 24.5 milliamps, and that's going to equal 490 ohms. Okay, so that's your minimum value for this resistor right here. The thing with these kinds of problems, you want to know your amount of your total current coming in, all right? And if you know this resistor, you know the voltage differential, you can easily calculate that. Then you need to know, if you're doing the minimum or maximum, you need to know how much the Zener is going to require to maintain regulation. And then all the rest of the current is going to have to go through your load resistor. All right. So that looks like it's going to be about it. I hope this video has been helpful to you to understand Zener diodes. Remember, the Zener diode is reverse biased in operation, and it's used to maintain a voltage. All right. And they are used in many places in circuits. Thank you very much, and see you soon.